Hello and welcome. In this series of lectures, I would be discussing about chapter number 3, which is the general purpose processors from the point of view of software. Now, as we talk about microprocessors, we can talk from the point of view of software and from the point of view of hardware. So this discussion would focus on the discussion from the point of view of software. So a little introduction as to what is a general purpose processor, and as we have discussed before, processor that is designed for a variety of computational tasks. So microprocessor is generic, right? And being generic, it is designed to execute lots of programs, lots of operating systems. So you might execute Ubuntu, you might execute Red Hat Enterprise Linux, you might execute Windows and whatsoever, and you might run different types of applications. So in fact, since the microprocessor is a general purpose processor, it has got to have lots of RAM and lots of resources so that all of those applications can be run really nicely. But surprisingly, it has got a low unit cost. Can everyone highlight why it has got a low unit cost? Because of high number of units that are produced. So for example, if Intel uses VLSI, which is a very expensive technology to make a microprocessor, Intel does not make 100 or 200 microprocessors. Intel makes billions and millions of microprocessors. So all that NRE cost divided by 1 million or 1 billion results in a low unit cost. But the microprocessor should be carefully designed because higher NRE is acceptable. So why is high NRE acceptable? Any student? Because of the previous point. We can have the highest NRE that we want, but we won't worry about the unit cost because we are going to be dividing that high NRE with the large number of units. So as a result, it would result in a low unit cost. And higher NRE acceptable because we want the best product to have the great performance, smallest size and smallest power consumption. And on the same hand, we have the low NRE cost as well. Now, can someone highlight why it has got a lower NRE cost? Any student? Because it is from the point of view of the user. If I want to make a processor based system, I just buy a motherboard, I just buy a microprocessor, and I am able to make state of the art system without spending a lot of time and money in a very affordable manner. And at the same time, I've got high flexibility, which means I can run different types of applications on it. So what does user do? User just writes software. User is not concerned about any processor design. So that is the reason why the NRE cost is low from the point of view of the user. So this point is related more to the user. Also known as microprocessor. Micro used when they were implemented on one or a few chips rather than entire rooms, right? And we also know that from previous discussion that microprocessor stems from the fact that when the processor started to be manufactured on a single silicon chip. So that's the idea. Let's now look at the basic architecture of a general purpose processor. Again, as I stated before, any processor consists of two principal components, the processor and the data path, right? The processor would actually consist of the controller and the data path. So what are the two parts of a processor? Controller and the data path. So control unit and data path. We note the similarity to single purpose processor, right? So single purpose processor also consists of two units, controller and the data path. Whenever we design a microprocessor, whether we might be designing from a different things like Verilog or VHDL, or we might be designing from HLS. Nevertheless, whichever the technology we use, the underlying system would create the two units, the controller and the data path. So what are the key differences between a microprocessor and a single purpose processor, right? So the basic difference is the data path is general. So in the case of the microprocessor, we have generic data path consisting of registers and a general purpose ALU. And what is the second difference? Control unit doesn't store the algorithm. The algorithm is programmed into the memory. So with the microprocessor, we have the famous stored program concept. So processes deal with the stored program concept. The program is not stored in the controller, the program is stored in the memory. That is the heart and essence of this stored program concept. Now let's look at some data path operations that we can do. We can have a load operation, and load operation read memory location into a register. So data transfers from memory to a register in a load operation. So after the load operation, the value of 10 is moved from memory into the register, right? Then we have the ALU operation. In ALU operation, certain input certain registers through the ALU and store back in register. So we might have an ALU operation, right, which is also called execution. Execution of instructions deal with the ALU operations basically. So let's say we are adding a 1 to this value, so this is the ALU operation, and the result would be written back in another register, or the result might also be written back into the same register. It depends on the program. So the value of 11 is written over here after the result of the ALU operation. Afterwards, we can have a store operation in which we write the register to a memory location. So in a store operation, value would move from an internal register to a memory location. So this completes the store operation. So it is a quick overview of some of the data path operations that we can have. Let's now take a look at the control unit. And the control unit configures the data path operation. This is the famous sentence that I have also been saying in my different courses like the microprocessor based systems course as well. And it configures the data path operations. So how does the control unit configure the data path operations? How? Any student? As a result of instructions. So whatever is the instruction, as a result of execution of that instruction, the data path operations are configured. We have this over here. The sequence of desired operations are stored in memory as instructions. So our instruction cycle is broken into several sub operations, each one clock cycle. So when we talk about the modern microprocessors, each sub operation of the instruction cycle is one clock cycle long. The first one can be fetch, which fetches the next instruction into the instruction register. Then we have the decode, finding the meaning of the instruction, like I always say. Then depending on the meaning of the instruction, if operands are required, the third sub operation is fetch operands, and which move the data from memory to data path register. After that we have the execute phase, which moves data through the ALU, like the +1 operation we just considered. And afterwards we store the results, we write the data from register to memory. So let's say we look at the fetch operation. Fetch gets the next instruction into the instruction register. PC, the program counter, always points to the next instruction. So generally after the fetch of any instruction, the program counter would automatically be incremented to point to the next instruction. And which register holds the fetch instruction? The IR or the instruction register. So let's say the program counter contained 100 and the instruction at location 100 was load R0, M500. So after the fetch operation occurs, this address is applied over here and the word, which is the instruction, is moved from the memory into the IR register. Then we have the decode phase, and decode phase determines what the instruction means. So we have a decoder, that decoder has not been shown, so the decoder would decode the instruction. Then we have the fetch operands. So after decoding the instruction, we know what the instruction is and we know whether the operands are required or not. If the operands are required, we move data from memory to the data path register. Now what the instruction does, it moves the contents of memory location 500 into the register R0, or loads the contents of memory location 500 into R0. So what happens? The contents of location 500 is 10. So after the fetch operand cycle, this value of 10 should be moved into R0. So this is the result of the fetch operands cycle. Execute means to move the data through the ALU. Now in this instruction there is no ALU operation, right? So this is a blank. The execute cycle does not do anything. Store results. Are we storing anything from a register to the memory location? No, because it's just a load operation. So nothing is done during this sub operation. Let's cycle through some instruction cycles just to have an idea. Our program is stored starting at memory location 100, and our program consists of 3 instructions stored in locations 100, 101 and 102. These are the contents of the memory, and we start, if we want to execute this program, the program counter should contain a value of 100. So the program counter is pointing to the 100 memory location. So we start execution. So during the fetch phase, what happens? The content of this 100 memory location, which is this instruction, is moved into the IR or the instruction register. What is the next phase? Decode. So as a result of decode, we find the meaning of this instruction, and after that we execute fetch operands, and fetch operands fetches the memory contents of location 500, which is 10, from this memory location into the register R0 as has been specified in the instruction. There is no execute phase in this instruction, so nothing happens. No store results, so nothing happens. And our program counter now is pointing to the next location, which is 101. So now after that again we fetch the next instruction 101, which is increment R1, R0, which means R0 is incremented and the result is stored in R1. So we decode this instruction 101. Nothing happens in this fetch operand because nothing is to be fetched. Then we execute the execute phase, in which +1 is added to this R0 and this 11 is stored in R1, just as the instruction says. Nothing happens in store results. So if we talk about this these two instructions, right, the fetch cycle was active, the decode was active, the fetch operands was active, execute was not active, and store result was not active. As far as the second instruction is concerned, the fetch is active, the decode is active, nothing was to be done on fetch operands, the execute was active, and the store result was not active. Now after this, program counter is pointing to 102, which is this instruction. So we fetch, we decode, no fetch operands is required, right, because it's a store operation. the value of R1 is going to be saved into the memory location 501. Nothing happens in execute, and of course the store result becomes active, where the value of R1, which is 11, is stored in memory location 501. So the last thing, we were active in fetch, decode. We did not fetch any operands, we did not do any execution, we only stored the results. So that is the idea for the last case. Some architectural considerations might also be involved, which are important architectural considerations. One of them is n-bit processor, right? True n-bit performance. Remember my discussion previously in my previous courses? So if you want to have true n-bit performance, that is true, okay? True n-bit performance, the ALU should be n-bit, the registers should be n-bit, the buses should be n-bit, and the memory data interface should also be n-bit. So when we talk about embedded systems, of course 8-bit, 16-bit and 32 bits are common. Desktop servers go higher, they might be 32-bit, 64-bit, and now we are also working on 128 bits. So the program counter size determines address space. So if you want to have more registers, if you want to make more complex systems, we must have a large program counter size. So in general we can say that this n-bit processor terminology is related mostly to performance. So if you want to have more performance system, you increase the value of n. You move from a 32-bit, true 32-bit to true 64-bit, so you'll have a lot of performance. If you move from true 64-bit to true 128-bit, you're going to be having more performance. But this, on the other hand, affects the complexity of the systems you can make. So if you want to connect lots of memory, lots of I/O into the system, you need a large address space. So you need a large program counter size for that. And for more performance, you can work on this n-bit process. So considering further the architectural considerations, we also have a consideration about the clock frequency. And clock frequency is inverse of clock period. So what is the condition for clock frequency? It must be longer than the longest register to register delay in the entire microprocessor. So when we are considering the frequency of operation of our embedded system, we should work on the longest delay, right? So memory access is often the longest. So our frequency would also affect the memory access. In fact, this point is very common and very important. Because of this particular point, we have the concept of cache memory. So cache memory attempts to decrease this memory access time so that the clock frequency can be increased. So caches goes a long way in affecting the clock frequency of operation of a particular embedded system. So here are the different types of delays: register to register delay, right? Register to ALU delay, and register to memory and memory to register delays. So this delay is basically the longest, so we try to minimize this delay by using the concept of the cache memory. So pipelining, an important consideration, and pipeline of course increases the instruction throughput. So if we want to increase the instruction throughput, right, or instructions per second, so we can have the concept of pipelining. So let's have a very usual thing and very lively example, right? So if we have a washing machine, so first we'll have the wash cycle sequentially, and after the wash cycle completes, then we'll have the dry cycle. So this is non-pipelined architecture. The first process must complete and then the next process starts. On the other hand, we can have the pipeline instruction execution, and this is basically a space-time diagram that has been shown. So this is the first phase, this is the second phase of instruction, third phase, fourth phase, and fifth phase. These are the stages: stage 1, stage 2, stage 3, stage 4, and stage 5. So at time point 1, instruction 1 enters this first phase, and in time point 2, when instruction 1 has entered the second phase, instruction 2 has entered the first stage. Similarly, at this point in time, instruction 1 is in the third phase, and instruction 2 is in the second phase, and instruction 3 is in the first phase, and so on. At this point in time, instruction 1 is in the execute phase. Similarly, instruction 2 is in the fetch operand phase, instruction 3 is in the decode phase, and instruction 4 is in the fetch phase, and so on. So as you can see, the total time of execution of the instruction has decreased when we use the pipeline concept. So over here, this is non-pipeline disk cleaning, and this is the pipeline version of disk cleaning. So we have this concept basically that in this particular process, less time is consumed. This concept is similar to the idea of conveyor belts, right, or assembly lines, where the task is divided into smaller tasks because of the way the instruction execution was divided into this fetch instruction phase, decode, fetch operands, execute, and store result. So it is basically parallelism, because in this point in time, instruction 1 is executing this phase, instruction 2 is executing this phase, instruction 3 in parallel is executing this phase, and instruction 4 in parallel is executing this phase. And so we have different concepts and different formulas of pipelining. I would advise the students to please look into it and revise these concepts.